Jai Hind, welcome to the course Network Analysis and Synthesis, and I am going to discuss about the network synthesis of this course. So, in the previous lecture we discussed the network synthesis of two elements type one port network. In this connection we discussed the LC network. LC network we discussed, and in this connection we can see that the synthesis can take place in two types of forms. One is the Foster form and other one is the core form. So, in the last class we discussed in detail about the Foster forms, and we have seen that if the network function is impedance, then we go for the Foster first, and when the network function is admittance, if the network function is admittance, we go for Foster second, and the technique is partial fraction expansion. So, technique is partial fraction expansion we consider, and what are the methods? Methods are removal pole at origin, removal of pole at infinity, removal of conjugate imaginary poles. So, out of four methods, and the fourth one is the removal of the constants. So, out of these four methods we use generally three for Foster forms of LC network. Now, the another form is that is the core forms, which is ladder development. What we do, we just carry out the continued fraction expansion of a given network function, and also core form is two types. One is the core first and other one is the core second. So, in the core first form, what we do, we carry out the continued fraction expansion about pole at infinity. So, if the function is given and you are required to find the core first, then you have to identify whether the given function is carrying pole at infinity or not. If not, then you have to make it. How will make it? We just invert the function. We will see later on. So, in the core first, we carry out the continued fraction expansion about pole at infinity. So, what we do, we carry out the long division. First, we arrange the polynomials, numerator and denominator polynomials in descending order, and then the divide numerator polynomials by the denominator polynomials once we find the pole at infinity. In the core second form, what we do, we carry out the continued fraction expansion about pole at origin. So, in this we also carry out the long division, and first we arrange the function in the ascending order, and then we carry out the continued fraction expansion. So, we will see later on in detail. So, this is another example. If suppose here the given function is impedance and you are required to find the Foster second. So, what we have to do, we have to just invert this function to make it admittance, because you have to find the Foster second. The Foster second is possible for the admittance function, whereas the given function is impedance. So, just we invert it and then we carry out the partial fraction expansion, and we can see that there are two conjugate poles. So, there will be two LC tanks, L and series will be L and C will be in series, and then will be in the parallel. So, we can carry out, and we just in the last class we discussed. So, we stopped here. In the last class we stopped. So, this is the Foster second. Second form of LC network. So, in the last class we stopped here discussing the Foster forms of LC network. today I am going to discuss about the core forms. So this is the your given network function fs in the form of the polynomials. So we can see that from the property of LC emittance function, the degree of numerator and denominator polynomial must differ by 1. It means it is the ratio of odd polynomials to even polynomials or even polynomials to odd polynomials. So there is a difference between, so m minus n is also always 1. So there may be a pole at infinity or there may be a pole at origin. So we take the first case when the m greater than n and fs is zs. Fs is zs, that is there is a pole at infinity. So what we do, just we carry out we can remove this pole by removing this inductor, then remaining function is still a LC function. So what we do, we just carry out the division, divide the numerator polynomial by the denominator polynomial. Okay, now the degree of this is, but the degree of numerator n minus 2, so this is, so again there is a difference, so we get this y2s 1 by z2s and so on. So in this case we can, every time we remove a pole at infinity. So each time we remove a pole, we remove an inductor or capacitor upon the function is impedance or admittance in nature. So this is the long division Zs, this is the first, if this is the impedance, then it will be impedance, admittance, impedance, admittance, impedance, admittance and so on. So first you have to identify whether there is a pole at infinity. You are going for the core first identify there must be a pole at infinity. If the function has, then arrange the function in descending order and divide the numerator polynomial by the denominator polynomial. So this is the general form of core first. This is the general form of core first. Core first for L1 C1 L2 C2 and so on. So inductor series arm, capacitor shunt arm. So this is the general form or first general. Okay. So if the Zs function being expanded has no pole at infinity, okay, then it has a 0 there because it is a ratio of odd to even. In such situation, the function is first inverted and then we proceed as usual. So what does it mean? It means the function must have a pole at infinity. If the function is Zs, suppose it is not having the pole at infinity, it means it has 0. So what we will do, just we invert this function to make pole at infinity and then we proceed as usual, means carry out the continued fraction expansion. So it is seen that the nature of the first element of the network is fixed by the nature of Zs at s is equal to infinity. The first element is inductor. If it has a 0 at s is equal to infinity, then first element is a capacitor. We invert it. So this is the theory, this is the technique behind the core first. If the given function is an impedance, then the first quotient must be an impedance. On the other hand, if the given function is admittance, the first quotient is an admittance and so on. Second core forms, that is the removal of pole at origin. So continued fraction expansion about pole at origin. So the lowest degree of numerator and denominator polynomial of LC function must differ by unity, that is pole or 0 at the origin. So S is equal to 0. So removing successive pole at S is equal to gives a network in second core form. So what is the technique? In order to remove the pole at the origin, we must first arrange both the numerator and denominator polynomials in ascending order in S. So in the core first we arrange in the descending order, in core second we arrange the polynomials in ascending order in S. So this way, if the function is given, what we do? Just first arrange the polynomials in ascending order, and we can see that a0 is 0, here a0 is 0, and then you carry out the continued fraction expansion. So this is, if this is the impedance, then this is the impedance, admittance, impedance, admittance, and so on. So we can find the elements L and C by just carrying out the continued fraction expansion about pole at origin for core second. And this is the general form. This is the general form of core second. C1, L2, C3, L4 and so on. Since the first term of the expansion is impedance, then must be admittance and so on. So impedance, admittance, impedance, admittance and so on. Now this is the theory behind the core first and core second. We just try to get out some examples to find the LC network in core first and core second. So here the given problem is, it is a impedance function, required to first find the core first and core second. So we can see that here power is 4, numerator polynomial, degree of the numerator polynomial is 4 and degree of the denominator polynomial is 3. So m minus 1 is equal to 1. So for core first, what we will do? Just arrange the numerator and denominator polynomials in descending order. So here this is in the descending order. And then the divide the numerator polynomial by the denominator polynomial. So here we can see that this is, here if we multiply twice s with this, we get this one, and we multiply this, we get this one. So we get this. Now divide this function by this. So first element is impedance, so this is impedance. This is the impedance function, because ZLC is impedance. Here we have inverted, so this is your admittance. Then impedance, again we inverted, and then admittance. Okay, we carry out the continued fraction expansion till we get the remainder 0. So here remainder is 0. So we can find out what are the elements. So if Z1 is, suppose it is S2 twice S, or it is a impedance, so it means whether it is inductive, so inductive impedance one is SL. So here L is equal to 2 Henry. Okay. So from here we can get the value of the inductor. Here this is the admittance. So admittance Z is equal to your 1 by SC or Y is equal to SC. Okay. So for the admittance, this is what is this? So this is, we compare, so C is equal to 1 by 12 farad. Okay. Capacity admittance is SC or capacity impedance is 1 by SC. So this is the admittance. This is the impedance. So here L is equal to 24 by 5 Henry. Here this Henry, and then this is your, so this is 5 by 36. So this way we can find the core first. So this is the core first form. This is your inductor of 2 Henry, this one, this value, then admit 1 by 12, this, then the inductor 4 by 5, this one, and this is the 5 by 36 as so capacitor. So generally the first element is inductor, and that is the series arm, and shunt arm is the capacitor. If the function is having at infinity, okay, and we are carrying out the continued fraction expansion about pole at infinity. Suppose this function has pole 0 at infinity. 0 at infinity, so what we will do, we just invert the function to make the function pole at infinity. So in that case, first element will be missing, this element will be missing, and we start from here. That is the cos second. Cos second is the removal of pole at continued. So continued fraction expansion about pole at origin. Okay. So in this case, what we do, we can see that there is a pole at origin, because S is equal to 0, S is equal to 0. So there is a pole at infinity, there is a pole at origin. So to carry out the continued fraction expansion about pole at infinity, we get core first. For cos second, we carry out the continued fraction expansion about pole at origin. So and this function has pole at origin, S is equal to 0. So what you have to do, we are just to arrange this function in ascending order. Arrange the function in ascending order. So this is the, so 18 plus 20s square plus 2s to the power 4, 4s plus s cube. So first step is, if we are going for cos second, remember, if we are going for second, arrange the polynomial in ascending order and then carry out the continued fraction expansion. So that is the long division. So again, this is the division. So this is the impedance. So this is impedance. If the function is impedance, so this is impedance, this is admittance, this is your impedance, admittance, and so on. This is the impedance. So what is this? So we can see that if we see the Z inductive, your capacity impedance, so ZC is 1 by SC. Okay. So what is, it can be written as, So S and C is 2 by 9. So if you compare this with this one, C is 2 by 9 farad. Okay. This is admittance. So admittance. So if this is inductor SL, 1 by SL. 1 by SL is admittance. It means L is equal to 31 by 8. This is your impedance. So C is equal to 30 by 961. So this is your C1, this is your L2, this is C3, this is your L4. So L4 is 62 by 15 Henry. 15 Henry. This is the farad, Henry farad, and so on. So this way we can get the chord second form. This is the, see that this is your 2 by 9, 2 by 9 from here. This is your 31 by 8 Henry, that is the inductor. This is the capacitor, inductor. This is chord second form. So we can see that this is the series arm. Series arm is capacitor and shunt arm is inductor. So this is the chord second form of LC network, two elements type, first port or one port network. So this is the chord second form of LC network. So generally in the chord second we have in the series arm we have the capacitor, in the shunt arm you have the inductor, and in chord first in the series arm you have the inductor, in the shunt arm you have the capacitor. So this is the general arrangement for chord first and chord seconds, provided the function has pole at infinity and pole at infinity. If the given function is not having pole at infinity, it means it has 0 at infinity, because there is a difference in degree of numerator and denominator polynomials, because it is the ratio of odd to even functions. So if you are going for if you are for the chord first, then first identify whether the function is having pole at infinity or not. If not, then you have to invert the function, because it means the function has 0 at infinity. So to make pole at infinity, we invert the function. So once we invert the function, that this element is missing, whether we are going for the chord first or chord second. Okay, first element is missing, so we start from the here, and this is the general procedure to find the chord first and chord second of LC network. So for the LC network we have discussed 4 forms: Foster first form, Foster second form, chord first form, chord second form. In the Foster first form, if the function is impedance, we go for the Foster first. If the Foster is admittance, we go for the Foster second. If the given problem, if the given function is suppose admittance and you are required to find the Foster first, then you have to make the function impedance to find the Foster first. If the given function is impedance and you are required to find the Foster second, then you have to invert the function to make it impedance to admittance to find the Foster second. And the technique is partial fraction expansion, nothing else. We carry out the partial fraction expansion for the Foster forms, whereas in the chord forms we carry out the continued fraction expansion, that is the long division. In the Foster form, what we do, we just arrange the polynomials in descending order if the function has pole at infinity, and then carry out the long division and we find the elements. In the cosecant, function must has pole at origin, if not then we make it. Once we find the pole at origin, we go for the cosecant, and to carry out the continued fraction expansion, what we do, first we arrange the polynomials in ascending order and then carry out the continued fraction expansion as seen here. So, this is the way to find the Foster forms and core forms of LC network. In the next lecture, we will carry out the RL impedance or RC admittance function to find the Foster forms and core forms of the networks. So, thank you very much. Jai Hind.